Good day, sir. This is my explanation for figure P.4.8 and P4.10. First, for figure P4.8, here we have a cantilever support beam which has a length of 14 feet, a rectangular distributed load of 120 pound per feet, and a length of the load of 8 feet, and that gives us a central singular load which is 960 pounds for the distributed load. And so next, the given problem. Here we can solve for the moment diagram by first getting the moment and the reaction forces of the beam. Here, by getting the concentrated undistributed load, we have 960 pounds and a measurement of 4 feet from the side to the single deconcentrated load, and the total distance of 14 feet. And here we have a reaction force RB and the moment for the summation of vertical forces at 0. RB is equal to 960 pounds. And for the moment, here we have a negative 960 multiplied by 14 minus 4, and that is equal to 960 pound-feet. And next, we need to cut the beam into segments. For the segment AB, you have a following 120, and that corresponds to the distributed load, and distribute for 4 feet and at X by setting the length of the beam AB or the segment AB into X. And now solve for the B or the shear force and the moment for the T shear force. You only need to get the summation of the forces for 2 equal to 0, and that gives us a equation of B squared negative 120x. And for the moment, summation of moment is close to 0, setting as a counterclockwise as positive. We get negative minus 120x multiplied by x minus 4, and give us negative 1 to the x squared plus 4 EPX. For the segment BC, here we have the total video of the beam. We have 120 multiplied by x minus 6. Since we set the distance from the side of the beam to the side of the rectangular lobes as 6 feet, and by setting the total length as x, we get the equation for the distributed level of 120 by multiplied by x minus 6, and we're now solving for the shear. And the moment, resetting the summation of forces vertical equation to 0, we get the shear force is equal to negative 120 multiplied by x minus 6 and 480, and that gives us a equation of negative 12x plus 720 rather. And for the summation of the moments, in order to get the moment here at this point C, we get negative 120 multiplied by x minus 6 multiplied by x minus x over 2. That is the distance from the concentrated load to point C, That gives us an equation of negative 60x squared plus 160. For getting the points to plot, we just need to substitute the values of x for the shear and segment AB. Here we have equation B is also negative 120x, and at the x equals s to 0, b is also equal to 0, and at x goes to 8, b equals to negative 960 that show in the graph. Here for the x equals to 0, we have 0, and for x of equals to 8, v is also negative 960, and for the segment BC, we have b is also negative 120x plus 720, and for x is equal to 8, we have b where the shear is also negative 240. And for x equals to 14, we get v is equals to negative 960 here. Next, for the moment, we have for AB equation, m moment is also negative 120x squared plus 4abx, and then at the x equals to 0, we have also a moment is equals to 0, and for x equals to 8, we have moment of negative 3840 as plotted here in the graph. Left 60x squared plus 2160. You get at x equals to 8, m equals to negative 1680, and then x goes to 14. M is equals to negative 9600, shown here in the graph. Now, this is the complete graph for the figure P 4.8. And let's go to the next problem. Figure P 4.10. We have here pin and roller support beam and a uniformly distributed load of 120 pounds per feet. So first, solve for this equation. We need to get the reaction forces at pin support and also the roller support, and by drawing the FBD. Here we have the central or concentrated load of 10,080, that is the 120 pound per feet multiplied by the total length of the beam, which is 9 feet. So 120 times 9 is also 10,080 pounds, and the drawing the reaction forces RB and RC. For the pin supports and also the distance given, so by setting the vertical forces equals to 0, the summation of vertical forces positive upwards, our B plus RC would be equal to 10,080 pounds, and then summation of moment is equal to 0, and counterclockwise as positive, that gives us a value of RB, and we get RB multiplied by this distance 6 feet is equal to 10,080 pounds multiplied by the distance here, which is 4.5 feet, and that gives us the direction of RB, also 810 pounds. For the RC, using the equation at the summation of vertical forces, we get RC is equal to 270 pounds. And okay, moving to the segment AB. Since we already have the required reaction process, drawing the FBD, here we have the distributed level of 120 multiplied by x, which is the total distance here, and for the shear force downward for positive, and the moment here counterclockwise for also positive. So summation of forces vertical is equal to 0, downwards positive. B would equal to negative 120 x and 40. Dimension of moment is equal to 0. M is equals to negative 120x multiplied by x over 2. Here, which is distance from this centroid or the central force here, that is equal to negative 60x squared. For the segment BC, okay, here we have the total given diagram here, which is the length is set as x, and given the lower 120x, we also have the reaction RB and also the RC here, and getting the shear force and the moment, we set the critical forces to 0, downwards positive, in order to get the shear force, and that gives us an equation of negative 120x plus 810, and for the summation of moments also 0, counterclockwise as a positive m is equal to negative 120x multiplied by x over 2, which is distance from the centroid here to point C, plus 810 multiplied by x minus 3, and that gives us equation of negative 60x squared plus 810x minus 2430 gives us a total of a value of 303.75 pounds for the maximum moment. And that's all.